This second example is very much like the first example, except we've got a pulley in here. So something that this doesn't make it really any harder, it's just kind of a different way to think about it. We have to think about, it's like we had the last example with two boxes side by side kind of being pulled one way or the other, but now it's wrapped around a pulley. So when we look at this, we kind of have to imagine what's the forwards direction, what's the backwards direction. So there's a jug, it's 7 kilograms. If I release this thing from rest, obviously the jug is heavier. The jug is going to go down, and at the same time the bucket is going to go up. So I'm going to focus on the pulley wheel. We can't really talk about up and down here. What we're going to talk about is clockwise, counterclockwise. So again, if the jug is heavier, the jug starts to go down this way, the bucket's actually going to go up this way. I'm going to call that my positive direction. Okay, so it's going to seem a little weird at first, but up for the bucket, and let's see, this is counterclockwise for the wheel, and down for the jug. All of that is my positive direction. That's all considered one direction. The opposite direction, so clockwise, that's going to be negative. Okay, so same idea. We're going to start this thing just like we did the last one. We're going to look at free body diagrams and say, well, this guy's got force of gravity of the jug. This guy's also got force of gravity of the bucket. What pulls the bucket up, the reason the bucket's going to go up and not down, is because there's this rope attaching it. Okay, so we've got, again, tension. This time I'll just use a capital T. We'll switch it up for some major fun. I'm going to look at the jug. Same thing. The jug is going down, but the reason it's not just free falling is because there's a tension force going up this way. Okay, so that tension, it's the same tension. It's a single rope. It does pass over a pulley, but single rope, that tension and that tension are the same. Sometimes people like to say like tension 1, also call this tension 1 because it's the same. If there were multiple things, if there was another rope and another bucket, we could have tension 2 in that second rope, something like that. So when I look at this then, I've chosen my positive direction. I've got all the forces. This is a free body diagram, just like we did in the last question, or very similar anyways. It's basically asking for the same two things. Okay, so I'm gonna do the exact same steps. It's just gonna look a little bit different because of the pulley. Okay, so we're gonna start off, we're looking for acceleration of the objects. This doesn't work every single time in every situation, but most of the time, if you're given a bunch of forces, you can find the acceleration of the objects by looking at the system. It's a good starting point, but it doesn't work every time, just so you know. I'm going to do F equals ma. Again, I'm looking at the system, I'm looking at everything, and just like we said last time, remember this tension here cancels this tension here. No normal force to cancel force of gravity. Remember, these objects are not resting on like a table or a surface, a floor or something like that. Okay, so no normal forces in here. There are tensions though because of those ropes. When I look at this as a system, remember the positive direction. Okay, so anything that makes the wheel turn counterclockwise, like this force right here, it's going to be positive. Any forces that are trying to resist that motion, like this guy right here, are going to be negative. Okay, so when I sub this stuff in, I'm going to say the force of gravity of the jug, the weight of the jug, subtract the force of gravity or the weight of the bucket equals mass times acceleration. Always ask yourself, what mass am I putting in here? And always answer yourself by saying, well, what am I choosing to look at here? Is it the system? Is it the jug or the bucket? If it's the system, so I always recommend writing something like this. Just one word is fine, but tell me what you're looking at, or remind yourself what you're looking at. This is mass total because it's the system. We need to find these forces of gravity. Force of gravity is always just mass times 9.8. Same thing over here, mass times 9.8. It's its own mass though. I'll put them in over here. So mass of the jug times 9.8. Here it's mass of the bucket times 9.8 equals, you could say this is the mass of the jug plus the mass of the bucket. So total mass times acceleration. Again, once you can get a line like this written, even really this line, but once you can kind of get this line written, the rest is easy. Now we're just subbing in numbers. So this is 7, this is 9.8. The negative sign is because this force is in the negative direction. Okay, this mass, 2.5, G, 9.8. Sometimes people ask about the G's, should they be going in as negatives or positives? This is always the magnitude. Okay, so when we sub in G, so mass and G, what we're finding is the magnitude of the weight, and then we're using this to decide the direction of force. Okay, so magnitude here, G is always going to be just positive magnitude. Here we've got 7 plus 2.5, so just 9.5. You don't have to show me that. You can just put in the numbers. Let's see, this one is 68.6 and 24.5 equals 9.5a. Again, you could just solve kind of directly if you want. Acceleration 4.6421. Acceleration approximately for sig digs, 2 sig digs, 4.6 meters per second squared. This gets a little bit tricky for direction. You could say down for the jug, up for the bucket. I'll generally default to this. I will say counterclockwise. People often will say like counterclockwise, or you can write out counterclockwise, or positive direction as shown on the diagram, something like that. Okay, so counterclockwise is good in my books. For part B, so again, same as we did in the last question, for part B, we're looking for the tension in this string or this rope, or the thread, I guess they call it. For the tension in the thread, I can't look at the system. I gotta choose a single object. Doesn't matter which one. I'll choose the bucket. So for part B, I'm gonna look at the bucket as we do this. We're doing F equals ma. The force acting on the bucket, so again, we're covering up, sorry for the shadow there, we're gonna cover up the jug. Hopefully you can see that. Pretend it's covered up, completely covered. You can put your hand over it. What we've got then is this force and this force. Again, if I look just at the bucket, I don't have that force. Okay, so imagine, I don't know, this is gonna be too much shadow. Imagine I'm covering that thing up. So I cover this guy up here, and we're looking just at this thing. If I look just at this, I've got 2 forces, there's nothing to balance them, either of them. Okay, so I've got that tension in the positive direction, right? It's going in this direction. This one here is resisting, so again, that guy is negative. The mass is only the bucket times acceleration. I'm gonna start subbing in some values here. This force of gravity is the same that we found over here. The mass of the bucket is just 2.5, okay, so not the system mass. Acceleration, again, use your unrounded value, 4.6421. That acceleration is in this positive direction. Okay, so that's good. We can rearrange this thing and solve tension 36.1 approximately. So tension, it's approximately 36 newtons for sig digs. And again, I'm gonna say that's magnitude only because we're just looking for this tension or this tension, either one, we're just looking for the number part of it.